Okay, so we're looking at taking the derivative, and the one thing that makes this look a little odd right now is that we have x's and y's both on the same side. Well, a little bit of algebra, I'm going to rewrite this in a standard form style. If I bring the 2x to the third over to the other side, now this looks a whole lot friendlier. And I'm going to start focusing on a new notation here, and you'll see why. So if I want to take the derivative of this whole thing, notice how I just put d dx. That stands for derivative. And then what we're going to do is we're going to take the derivative with respect to x of every function. Well, the derivative of y is 1, but it's dy dx, and that's where the dy dx comes from. And then it's just the power rule. 3 comes down, multiply it together. The derivative of negative 4x is negative 4, and the derivative of 15 is just 0. So here's my first derivative. Okay, but then they asked me to take the second derivative. So watch what happens with this notation. Actually, I don't want to box that around yet. What if I take the derivative of this again? All right, well, what happens? Well, d times d gives me d squared, and then the y is just going to stay. Dx times dx is actually dx squared. Notice how why we put the 2 where it is here and the 2 where it is here. It's because we're taking derivative with respect to x again. And then this is just another power rule. The 2 comes down. We take 1 away. And then we have our constant negative 4 to the derivative of that is 0. So I have my first derivative and my second derivative right here. All right. This, by the way, is called explicit differentiation, which means you're explicitly solving for, or you're taking the derivative for x. Today, we're going to run into some problems where we can't really split x and y up, and we're going to learn an implicit method of differentiation, and that's the big idea today. So all this work, everything we've done up to this point, this entire year, has been explicit derivatives. All right, and then you're going to have some problems like this in the homework tonight that involve radicals or rational roots. So what we have here is I've got the cube root, and this does not look friendly right now. So we're going to rewrite this, and instead of doing the cube root, we're going to actually take it to the 1/3 power. Well, then if you look at that, hopefully that is screaming chain rule. You've got the outside, and then you have the inside function. So we have to do the chain rule again. So now I'm going to take, and let's use my new notation. I want to take the derivative. So I'm just going to take the derivative of this whole thing with respect to x. Well, what does that do? That gives me dy dx, which just is our notation for derivative. Then I've got the chain rule. I have to take the derivative of the outside, so the 1/3 is going to come down in front. And then I'm going to take 1 away, but when I take 1 away, it's fractions. I just want to kind of subtract that creative form of 1. So 3/3, well, when I do that, 1 minus 3 is negative 2/3. So there's the derivative of the outside. Now we're going to keep the inside exactly the way it is, and then we're going to multiply. Notice I'm putting parentheses. I may need them, I may not, by the derivative of the inside. Well, that's just a quick power rule. The +2 is going to be put there as a 0. So technically I'm done. You could stop right there. However, we do want to get used to just algebraically simplifying it. What do I have? I have 1/3. I'm going to put the divide by 3 down here. I'm not going to put the 1 because this 1 is going to times by a 7x to the 6th. So I'm just going to put that up top. And then I've got the negative. Well, that negative is going to put the original piece down in the denominator. And most likely this is what your answer would look like. However, that 2/3 could be rewritten like this. So see in the 2/3 we have the divide by 3. Well, that divide by 3 is the same as the cube root. So that's where this 3 divided by 3 goes. And then the blue square, that's going to stay in the inside just the way it is. So this is most likely what it would look like on a multiple choice problem, but any form that we've stopped up here is officially accurate and correct.
Isn't it like a rule or something where like we shouldn't have our roots in the like denominator?
Um, the rule that we almost always want to abide by is you should always, if you have a negative exponent, it should always be rewritten so it's in the denominator.
So it
The
like overrules the other one?
Oh, I see what you're asking.
Yeah.
I got you. This is, yeah, that's a way back in geometry. That
Uh-huh.
was if we were dealing with, so let me just as a side note, like let's say that I had an answer of x equals 16 over the square root of 3, where we said we don't like roots in the denominator. We don't care here. This is actually better. But in this case, we could rationalize the denominator, and then that would turn into the square root of 9, which is 3. So I think that's what you're thinking,
Yeah.
where you get that at some point, it's just manipulating algebra, and we're not even doing calculus at that point. So we don't want to make it that confusing. So we're not going to do that, especially with derivatives.
Okay. Just like in like our AP tests or anything, they're not gonna expect us to do that, right?
No, only if it was an answer, but see how we have equations here? So if we didn't have any x's, they may ask you to reduce your answer, but this is an equation for a derivative, not an answer.
Oh, okay. Okay.
Yep. And
Got it.
I'll as best as I can, I'll point that out every time it comes up. So all right. Really quick, I want to make sure that you guys are aware of this. And I just put this on our Schoology page again because we've got let's see if I can find it. We've got a handful of people that didn't sign up yet. So if you go to our course, and don't do this now, this is something you can do tonight, tomorrow, Wednesday when we don't have school. But under this week, I put an extra little sign up piece. So sign up for the AP Classroom, click here for step-by-step instructions, and then here's our code for us to join. Now, here's the thing. If you don't do this by like November 12th or 13th, we have some time, but if you don't sign up for it and you want to take the AP test, then after November 13th, I think it is, you have to pay $40 to register. That registration is wiped out now, but you'd have to pay for it. Um, that you have to pay for it to sign up at that point. So all you do is click on the directions. It walks you through step by step. You were supposed to do this like 4 weeks ago, 5 weeks ago, and half of us did, and the other half didn't. All right. Now here's the thing: sign up for it. It is free to cancel this year, which means if you don't want to take the test or you end up dropping calculus for some reason, then you don't have to pay for it. But if you aren't signed up and you want to take it, then you have to pay $40 for the late registration. So it's that's why I want you guys to sign up for the AP test, and then it's always easier to just cancel it, especially when they're not charging a cancellation fee this year. Okay, so make sure that gets done this week. I also want to give you a quick little view of what do we have going on for the rest of the trimester. So we're right here. We're going to do 3.2 implicit differentiation. And then we don't have school the next 2 Wednesdays, which means you will not be assigned homework, but those would be great days to get caught up on any missing work. All right. Now look at the title. We're going to do 3.2 on both days. So we're spending 2 big full days on implicit differentiation. And then we've got one section, kind of two left over, derivatives of logs and inverses. And then we're going to do a review, and your test will be on November 9th or 10th, depending on what day you have it. And then we just have like a week and a half left where we're going to do part of chapter 4. And we are going to have a final, but it's just going to be official, like a test. And it's going to be a mixture of units 1, 2, and 3 and part of 4 thrown in there. So that'll be taken on either the Monday or the Tuesday before our Thanksgiving break, which is the end of the trimester. So a lot of things are coming up fast, and before we know it, we're going to be done with trimester 1 already. Just so you know. Okay, so here's what we got. We're going to start off with implicit differentiation, and I usually don't offer step-by-step instructions to how to do these problems, but this actually lends itself quite nicely. So I'm going to ask that you write this down, and then we'll show you how it works and why we do what we do. But it's titled Implicit Differentiation. Well, implicit is what happens when x's and y's are mixed together, and we either can't solve them for y, or we don't want to. And then the word differentiation means take the derivative. So what do? We take the derivative with both sides with respect to x. And then we've got a special term here. So somebody just asked, what percentage of our grade is the final? It's going to be a 50-point test, just like every other test. So the final isn't more weight. It's just a 50-point test like we did every other one. The only difference is it can have questions from unit 1, 2, and 3 on it, as well as 4. But think of it. We've been using that stuff over and over and over again. So if I ask you to write the equation of a tangent line, that should be something that we've mastered now. Or if I ask you to find a quick derivative, you should be very well in tune. So yes, it's cumulative, but you're going to notice that we've been practicing all that for a while. So anyways, it's 50 points. Okay, so then we have to collect terms with the dy dx. This is an interesting piece, and this is the new part today. So we'll really get used to that dy dx. And then we have to factor out, so we're basically getting dy dx by itself. And that's it. So it's easy, it's tricky. Now it's easy, but it's tricky, and that's why we need practice. Remember what dy dx stands for. Right? And that's one thing kids often forget. When we solve for dy dx, that is the derivative. Well, the derivative is a slope. And if you know the slope, we could most likely ask you to solve this problem or use this problem to help us find the equation of a tangent line, maybe finding horizontal tangent lines, vertical tangent lines. So we can ask questions based off of the work that we're doing. All right, I'll give you a second to get caught up here. So we're actually going to take another look at the example that we just did in the warm-up, and we're going to use that to find dy dx, but with the implicit differentiation, which means, see how x's and y's are on the same side? We're just going to leave it just like that, and we're going to take the derivative with each piece. So this part here gets a little tricky, and you just got to make sure you really pay attention and follow the exact steps that I do. And I'm going to point out a little bit on how you could save some time once you become really good at this. All right, so what do we have to do? We have to find the derivative of both sides. Well, when we differentiate, we're going to call that d dx. Right? It's taking the derivative of both sides. So what I'm going to do is I could do it to the whole piece, or I could do it to both sides. And I believe writing it this way is the proper notation versus like I did in the warm-up where I just took it of everything. But I don't think it's that crucial. Now here's the tricky part, okay? We have to take the derivative of both piece with respect to x. So the derivative of 2x to the third, the 3 is going to come down, and that's going to give me 3x squared, just like we did before. And then there's officially, we're taking the derivative of x with respect to x. So see how it says dx over dx? Well, dx divided by dx is really going to turn into 1, so you don't have to write this part. Okay? But I'm gonna write it, and I think I did on all the homework too. But now I have to take the derivative of y. Well, remember, this is y to the first power, so technically the 1 comes down. And then I'm going to take the derivative of y with respect to x. So now notice this is dy dx. This is not the same as dx dx. So the dy dx does not go away, and that's actually what we're trying to solve for. So that's why it's important to think of that. Now I'm going to take the derivative of 15. Well, that's just 0. You don't have to write that. And the derivative of 4x is 4 dx dx. So notice, when I'm taking the derivative of something with an x, it's a dx dx. When I'm taking the derivative of something with a y, it's dy dx. Okay? Now what I usually do then is, since dx dx is the same thing divided by itself, that really just turns into 1, which is why we don't have to write it, because it's going to turn into 1 times negative 4. So there's nothing really too crazy there. And what's left over then is dy dx times 1 is just dy dx. 6x squared now. Now we have to, well, in this case, we don't have to factor out a dy dx because there's only 1. But step 4 is solve for dy dx. So then I have to just move that negative, I'm going to subtract the 6x squared. And there's my derivative. Okay? Now, you might be thinking, Strub, why would we do this when in the warm-up I just moved this over and I took the derivative without all this extra stuff? And you're right. For this specific problem, I wouldn't do it that way. But what happens when you can't do it? And that's what today is all about, is showing you those examples. Okay, this is kind of interesting. We want to find the derivative of So how did we get the dx dx right here? Well, think of this. We're taking the derivative of the function with respect to x. So the dx is on the bottom. That's going to be there for every piece. But then because this x is, the function is in terms of x, that's why we put an x here. That's where this x came from. So it's dx dx. And this function was y, so it's dy dx. So anytime you're taking the derivative of something with an x, it's going to be dx over dx. When you take the derivative of something with a y, it is dy dx. And every single time, the dx's are going to reduce out to 1. So some students don't even write those. But the dy dx never reduces out. Okay. How did you get the exponent to go from 2 to 1? So, not sure, 2 to 1 exponent. Not quite sure. This, if we're talking about exponents, this is 3 comes down times by 6, and then 3 minus 2 is 1. So that was always an x squared. And then here, the 1 came down, and officially we took 1 away, so it's y minus 0, which is 1. So that's why the derivative of y goes away. It turns into dy dx. I'm not sure, that last answer, I'm not sure, or a question. Above your answer looks like, is this one right here? Oh, it's probably just sloppy writing. Let me see if I can. This should be a 2. I think that might be. So this is a 2, 2, 2, 2. Okay. Hopefully that's where it is. All right. So now they asked me to take the second derivative. Well, what do? We're going to take the derivative of this function, and I'm just going to show you notation. I actually wouldn't write it like this other than showing you notation. So I'm going to take my answer, and then we're going to take the derivative again with respect to x. Now notice, this will give us more evidence why the 2's are in the spot they are. All right, so I'm taking the derivative of both sides. And what do we get? Notice there's a d times a dy. Well, d times d is d squared, and there's only one y. But then I have a dx times a dx, and that's equal to dx squared. So that's where this notation comes from. And then we're just going to take the derivative of each piece. So now we're going to take the derivative of negative 6x squared. Well, that 2 is going to come down. Officially, there's an x. And then because we're taking the derivative of this function and it has an x in it, that's where the dx comes in. And then this is a 4. And the derivative of 4 would be officially 0, so we don't have to write that in there. So then my final answer is just negative 12x, and the dx, those are the same. They reduce down to 1, so we don't have to write it. Now there are going to be times where I'll have y's over on this side, and if I have a y on this side, something special is going to come up, and we'll talk about that as we get to it. All right, you're going to have some questions here, okay? And my advice would be, let's go through a couple examples, and I bet those questions will be answered. So, you know what I'm going to say? Don't write this down. Don't write this slide down because we're going to do a bunch of them today that I just want you to watch. All right? So just take a look at how we do implicit differentiation. And first off, how do I know that I have to do implicit? Well, look at how messy this y is. Right? There's a lot going on with the y. I could try to move it all over to this side and solve for y, but it's going to get ugly. And it's not going to be friendly. So when it's not friendly, that's where the implicit differentiation comes into play. So what am I going to do? I'm going to take the derivative of both sides with respect to x. Well, the 7 is going to come down, and then I'm going to take 1 away. Nothing crazy there, but it's the derivative with respect to x, because this is an x. So that's where the dx comes in. That's going to be 1, so you technically don't have to write that. But now I have a chain rule here, and this is the tricky thing. So what's going on? I've got an outside function, then I've got an inside function. And I have to find the derivative with respect to y. So the derivative of cosine is negative sine. Keep the inside exactly the way it is. But then I'm going to times by the derivative of the inside. Well, the derivative of 3y squared is 6y. But then notice, what did I do? I took I took the derivative of y. So there's where the dy dx comes into play. Well, what's going to happen? Dx turns into 1. And then I just have to solve for dy dx. So I need to get this dy dx by itself, which means all of this is times dy dx. I'm going to just divide both sides by this whole piece. Okay, so what's left over is 35x to the 6th on top, and then I'm going to divide by this whole piece. Minus sine 3y squared. And you could write the 6, they actually might. I'm going to sneak that in between the negative, because 6y times negative is negative 6y. And then notice the only thing that's left over is the dy dx. And we could try to divide this out. If this was divisible by 3, good, but there we go. All right, so it looks crazy. Let's do another one quick just so you guys can get the hang of this. Sometimes there's ways you could use algebra to split up problems like this. And I'll show you that on this one. So don't write this one either. But what am I going to do? I'm going to take the derivative of both sides with respect to x. Now notice there's a chain rule here. I have my inside, outside function. The outside function is the e. The inside function is x plus y. So the derivative of the outside is just e to whatever it is. So in this case, it's e to the x plus y. But then I have to multiply by the derivative of the inside. Well, the derivative of x is 1. You don't have to write the 1, but you could. It's dx dx. Plus the derivative of y is 1 dy dx. And then that has to equal the derivative of the other side. Well, this other side, the derivative of y is 1 dy dx. So here's the tricky part now. I have to solve for dy dx's, and I have 2 of them. They both have to move over to the other side, but we have to use proper algebra to do so. Well, what's happening? This is being protected. So I need to first do some algebra to distribute. So I'm going to times, let's see if I can get my colors correctly. So e to the x plus y times 1 is just e to the x plus y. That's the first arrow. Now notice, I don't have to write dx dx is 1, so this whole thing is 1 times 1 or 1, and that's why I get this first piece. And then I'm going to do e to the x times 1 dy. So x, y. I might just put that whole thing in parentheses. And we usually don't write a 1 out in front, although you could. So that's the first step. And then I need to move this piece over here. So this whole thing is just going to move over with subtraction. And then the only thing that's left over on the left side is the red e to the x plus y. So what do we do now when I have more than one dy dx? Well, we have to factor. And that's usually where kids make a mistake or they forget to do this. Both of these two pieces on the right side have a dy dx. So I'm going to pull it out. And when I pull away a dy dx from here, you're left with a 1 minus e to the x plus y. Now I have 1 dy dx, and almost every single time you're going to have to factor so it looks like this. And then the last step is to get dy dx by itself. So what do? I clicked the wrong button on my pen. I'm going to divide both sides by 1 minus e to the x. E to the xy. I'll just do that in a different color. So if I divide, instead of times, if I divide it, it moves this over to the other side. And there is the derivative. And I know you're not confident in this yet, so don't worry. Okay, just hang tight. We'll get there. Okay, I do want you to write this one down because we're going to use implicit differentiation. So we're going to use this skill to help us answer some questions about the function. So when does this function have horizontal tangents? And then when does it have vertical tangent? We'll answer both of those questions. Well, I want to think about what do we know about a horizontal tangent? Well, tangent lines have slopes. If it has a horizontal tangent, then we're looking for when is the derivative, when is dy dx equal to 0? We've done that a lot. The only difference is now I have x's and y's on the same side. And this one, yes, you could solve it algebraically and do the derivative, but it would take a whole lot longer and it wouldn't be as nice. So what we're going to do is we're going to take the derivative with respect to x, and we will always do it with respect to x unless it's like a motion problem and the input variable ends up being like a t for time. So think of taking the derivative of each piece. Well, the derivative of x squared is just 2x, but then it's with respect to x. So dx, which, yeah, that's going to go into 1. Okay. That's not that important, but the next one is critical. Take the derivative of y squared. Well, the 2 comes down, and we're left with y to the first power dy dx. It's the derivative of y with respect to x. And then 25 is just a constant, so that's 0. So then our goal is to get this dy dx by itself. And that's just algebra. I would now say dx is just 1. And you might be thinking, why do I want you to write that? Well, the reason why is if you get so used to just taking the derivative, you're going to forget about the dy dx. And that's the part that students miss. My students that write this every time and reduce it out tend to not forget about it when you do y. So it's a little bit annoying, but I think it's worth that extra hassle. All right, well, this is 2x. What are we going to do? We're going to move the 2x over to the other side with subtraction. And 0 minus 2x is just minus 2x. And then I have to get rid of, this is 2 times y. So we're going to divide both sides by 2y. And then algebra allows me to simplify. You guys can see what I mean with my 2's. I don't know why I do this, but I write my 2's in 2 different ways, and I just tend to mix it up whenever. I don't do it intentionally, I can tell you that. Well, the 2's are going to go away, so I get negative x over y. All right, so that's just finding the derivative. Now let's actually use that to find horizontal tangents. Well, that's when the derivative is equal to 0. So I'm going to take dy dx and I'm going to put it equal to 0. We'll do that in blue. And then that has to equal whatever my derivative is. It could be friendly like this, or it could be really nasty. Well, how do I solve this? A fraction is equal to a number. Let's make it a fraction equaling a fraction. Now you're just going to cross multiply. So 1 times negative x is negative x, and 0 times y is 0, which, here's a little hint. Anytime you're finding horizontal asymptotes, it's whenever the numerator is equal to 0. And in this case, if I just divide by a negative, I get x equals 0. But this isn't the, it says when, this isn't the location, right? This is just the x value. So once I do that, we got to find the y value that corresponds with when x is 0, and that's where the original problem comes in. And so once I solve and I figure out what my x's are, I'm going to plug in to the original problem. I'm going to plug 0 in for x. And then it's just algebra. We end up with y squared equals 25. Well, what if I take the square root of both sides? I get 2 answers. I get a positive 5 and a negative 5. So there's where my horizontal tangents occur, at those 2 points. And if you know anything about this graph, it will hopefully make sense. Okay, what about the vertical tangents? This is where we have to really think about what makes dy dx undefined. when is the derivative going to be undefined? Because that's what happens when you have a vertical tangent. Your slope is something divided by 0. Well, you're going to take dy dx, and what can we not have? We can't have a 0 in the denominator. So I want to basically figure out what's going to make this, and I really don't care about the top. You could put a 1 here, it doesn't really matter. But that's kind of confusing. It's basically saying when is the denominator 0? Maybe I'll just do that. I don't want to show you a cross multiply, but what makes the denominator 0? That's a better way to think of it. Well, 0. If y is 0, I can't divide by 0, therefore I have an undefined slope. Remember, dy dx is slope. So that's my y value, but now I have to find the x that goes along with it. And that's just in the original problem. And you could probably do this in your head. You're going to get x squared equals 25. You can do that in your head. You don't need to show any of this work. All right, really quick extension. You don't even have to draw this. Going back to pre-calc, kind of. If I was to graph this, x squared plus y squared equals 25. Well, 25 is the same as 5 squared, which is just the radius of a circle. Right? So this equation, you'll have to really pretend that this is a circle, a perfect circle. But look at the points that we just found. At over 0 up 5, over 0 up 5, what do I have? I've got a slope that's equal to 0. At over 0 down 5, that should be a negative 5 there, I have a horizontal tangent, right? I've got a 0 slope. That's these points that we found above. Well, what about the vertical tangents? At 5, 1 or 5, 0, dy dx is undefined. Right? And then same thing here. Dy dx is undefined at those points. And you can quickly see the vertical tangents and the horizontal tangents. And that just gives visual evidence as to why we just did what we did. All right. I want to do one more problem, and let me see what we got here. Let's do this last problem, and I might, wow, where did the time go? We officially have 5 minutes left, so Mr. Holm, if you want to go spray the desks for those students that are at Tartan, you can do so.
Where do you
Just
guys want to see the numbers? There's only four I can remember
oh, okay.
where they are.
Sure.
At the end of the day here.
Yeah, and that if you just spray it down and it should be fine then.
Right.
Okay, so what do we need to write the equation of a tangent line? We need a point and we need a slope, but the connection with what we're doing today is right here. Slope. Isn't that the same as dy dx? So I just need to find dy dx, and notice I've got a lot of things going on here. And I don't have the room to write it for both. So I have to take the derivative of this whole mess. Well, the tricky part is you have a product rule here. And product rules do occur when you have a problem like this. Okay, now I apologize because this is going to go kind of fast, but let's do the product rule. The derivative of the first, well, the derivative of 2x is just 2x dx times the original second, that's just y, plus the first function u times the derivative of y, which is just dy dx. So this is the product rule that I just wrote down. And then I have to take the derivative of sine, or pi, times sine of y. Well, notice pi is a constant, so that's going to stay. The derivative of sine is cosine. We're going to keep the middle. And we have a chain rule here, because what's the derivative of y? It's dy dx. I want that in red. And then over here, we're taking the derivative of 2 pi, which is just a constant, and that's 0. So notice the product rule can still be applied. And then I just have to solve for dy dx, which means anything that doesn't have a dy dx, we're going to subtract over first. Now keep in mind, that's equal to 1. Right? So 2 times 1 times y, that's going to be 2y, and I'm going to move it over to the other side, just with subtraction. And then what's left over are both pieces here, but they have a dy dx in common, so I'm going to factor that out to start. I'm almost done, so please hang tight with me. So notice how I pulled the dy dx away from each one of these, which means the very last step then is to divide by 2x pi cosine of y. What is that? That's my slope. But now I need to find the slope when x is equal to 1 and pi, y is pi over 2. So look at the notation here. Okay, we know what dy dx is. Now I just have to evaluate that at the point xy. And that's the point that they gave us. So wherever I see a y, I'm going to plug in pi over 2. Wherever I see an x, I'll plug into 1. So here's the thing. It's 12:10. If you have to go, the homework is on. I'm going to come back to this. I got another couple minutes, but the homework is on our Schoology page. You can just do that. It's in the textbook. These answers are worked out completely, so do as much as you can. And we're going to do more of this on Thursday. But I'd like to finish this quick if you've got an extra 5 minutes. All right. So all I'm going to do is plug in I'm going to plug in 1 for x, so there's an x here. And then I'm going to plug in pi over 2 wherever I see a y. And then we evaluate. Well, the 2 over 2's go away, and I'm left with negative pi up top. And on the bottom, the cosine of pi over 2 is go over 0 up 1. So the cosine of pi over 2 is 0, which just leaves negative pi over 2. And there's the slope that we're looking for. So then my final answer, write the equation of the tangent line. We need the slope. And then we need to use the 2 given points. And we're done. Okay. That was really quick. I think I'm recording this. Something's happening weird with my recording. But I will post these worked out solutions on our page. And then here's the homework tonight. Right here. Okay, it's in the textbook. I'll be available from 1 to 2 o'clock for my office hours today if you have any questions. And over the next couple days, I'm going to be updating my grades with everybody that turned in late work over the weekend. So